Hey guys, welcome to this virtual lab for ECMN 215. I've tried to combine the TRIAC and SCR lab into one lab sheet, and we're trying to get to this so we can get through it and talk about three-phase rectifiers, which will be the next lab and the next video that we do. So in general, a couple of the things that you should have reviewed through the theory course about SCRs. So SCRs can be used in AC and DC circuits. Keep in mind that SCR stands for silicon controlled rectifier, also commonly referred to as thyristors. So you can see these in common applications. A lot of them, and when they're used in AC circuits, they are used for voltage control to a load. If anyone ever has or has seen an old school lamp in your grandparents' house or your parents' house maybe, they're used in lamps where you touch the metal of the lamp and it actually helps the lamp come on. You touch it again, it'll allow it to get brighter. You touch it one more time, it gets to its full brightness, and then you touch it the third time and it goes off. So what you're actually doing there is you are giving the circuit a little bit of a charge that will supply energy to the gate terminal of the SCR. By supplying energy to the gate terminal of the SCR, you allow it to trigger the gate at different points and pick up the sine wave depending on where it's triggering. So down below here you can see a graph taken with an oscilloscope where the full incoming sine wave is the white line, and then right here we're triggering the SCR to pick up the sine wave at about 50%. So two things. One, with just one standard SCR in an AC circuit, it's going to act as a rectifier, which is exactly what it is, a silicon controlled rectifier. It's made up of a few PN junctions, which we talked about with diodes, and the gate is actually tied into one of the P-type or N-type materials, typically the P-type. So when it was used in the earlier VFDs, it's a little bit better at controlling voltage in a DC circuit. Typically, it's triggered by an integrated circuit in a VFD that will tell it when to pick up the sine wave. You'll notice that these are all different types of SCRs. These can also be TRIACs. So they're very, very similar devices. And a TRIAC is actually two SCRs connected in parallel with the gate terminals tied together. That'll allow the TRIAC to trigger both pulses out of the secondary of a transformer, allowing for full wave control to a load. We could see that here. In this circuit, the TRIAC is connected. We have a second one in series with that gate, which allows the terminal to trigger it on and off, giving a higher value of voltage to the load. Okay, and first for this lab, we're going to look at SCRs. So if we come up here to the top of the lab sheet, okay, you put your lab number, the name. You should be able to click right in those boxes and fill in that information. So this lab will explore the testing and operation of an SCR in a DC powered circuit. It will also look at how an SCR can be used in an AC powered circuit and how TRIACs are used similar to SCRs in AC circuits. Procedure A, by connecting the SCR in series with the resistive load, we will aim to see how it can be turned on and off in a DC powered circuit. You're going to go ahead and connect the circuit shown below, if we were in lab, obviously. So the circuit objective, much like the transistor, the SCR needs a small gate signal or gate current, right? And the transistor, we call it a base signal. This is what allows the SCR to initiate current flow in the circuit. Once the circuit has been approved, we're going to energize the circuit and apply 20 volts DC to the SCR itself. Once it's on and you close S1, so once we have 20 volts measured between the positive and the ground or the negative of the circuit, with the DC voltmeter across the anode and cathode terminals of the SCR, we're going to close switch 1. And we'll observe that almost all of the circuit voltage of 20 volts DC will drop across the SCR. So in this line right here, when you close the switch and measure and record the following voltage at the anode and cathode junction, you should see supply voltage of 20 volts. With the switch closed, you're going to record 0 current flow from this ammeter, right? So if we're dropping all of our voltage across that anode-cathode junction, that should mean that it's an open circuit or an open loop and no current is going to flow. Here you should note what you noticed. You should notice that there's no current flow through the load. There's no voltage drop across our load. And it kind of gives you those notes right after it. So we'll move on to the next one. By touching the lead connected to R3, which is the 1 kilo ohm resistor, to either the closed switch or to the anode terminal, you'll be able to turn the SCR on. So let's take a look at that. If I take this terminal right here and I touch it to this closed switch, or I touch it to that anode terminal, I'm actually going to allow current flow through the resistor, which is a 1 kilo ohm, to the gate. Now, this is not a huge amount of current flow, and we're gonna see why this matters in the next portion of the lab. So it's just similar to the transistor, where it takes a very, very small amount of base current to allow a much larger current to pass through its collector emitter. The SCR will only require a small amount of gate current to allow it to do what's called latching. So once it latches, it'll allow however much current needs to flow through its anode cathode in a DC circuit. So by touching the lead connected to R3, the 1 kilo ohm, and to the closed switch or anode terminal, you'll be able to turn the SCR on. At this point, you should notice that all the voltage drops across the resistive loads further down the line from the SCR, and the voltage across the anode and cathode should only be about a volt. What does that mean for power dissipation? Well, determined by the load resistance, the current flow through there, and the voltage drop across the SCR, you can calculate the amount of power dissipated. Here, we're going to see about 1 volt dropped across the SCR. You're going to see minimum resistance across our resistive load. Okay, so if we have a 100 ohm resistor and we're measuring 20 volts dropped across it, or 19 volts dropped across it, we should see almost 2 amps, right? So 200 milliamps. Okay, you're going to record that theoretical current and voltage in these two places right here. So we should see about 1 volt across the anode cathode. The DC ammeter at this point, with minimum resistance in the circuit, should be measuring about 2 amps or 200 milliamps. What are we noticing about the circuit? Well, the circuit is now on. It is now conducting current flow and allowing voltage to drop across its resistors. The next step that we're going to go to is 11. Now we're going to observe how the SCR will stay on until the current flow in the circuit is decreased to a point that will cause the device to turn itself off. Slowly increase the load resistance to its maximum. You could actually do this one of 2 ways. If you decrease the supply voltage to a point where current flow will drop to a significant point, or if you increase load resistance, that will also decrease current flow through the SCR. By doing that, we're going to observe the DC ammeter. You will record when the device reaches its on-latching/latching point for the gate current. The on-latch or latching gate current is typically 10 milliamps or somewhere in that range, tens of milliamps. So we're talking 10, 20 milliamps is what you'll need to get the gate to latch. Okay, and then once the gate is on-latched, if you increase or decrease that resistance again, trying to allow more current flow, or if you increase that supply of voltage trying to create more current flow, once the SCR reaches the on-latching point and it turns itself off, it's now going to act as an open switch again until the gate is triggered one more time. So you can see how if we were trying to use this as some type of rectifier for an AC circuit, we'd run into a problem where it needs to be turned on over and over and over again. We're going to look at that in the next circuit. Okay, so procedure B, keeping in mind that the SCR is a rectifier, its operation in an AC circuit will act much like a single-phase rectifier. This, coupled with the fact that it needs to have its gate terminal triggered in order to conduct electricity, is how it can be effectively used to control voltage to a load in an AC circuit. By triggering the gate with different magnitudes of signals, the SCR trigger point will vary and pick up the AC sine wave at different points. So we're quite literally chopping off half of the sine wave, the positive pulses of that sine wave. If we were to connect a second SCR in parallel to this one, we would actually be creating a TRIAC, which is a full wave rectification and voltage control to a load. Okay, so this will ultimately change the value of the effective voltage to the load. So once you construct the circuit, again, we're going to close that switch, that S1 switch. We're going to set the amount of resistance for R1 to 50 kilo ohms in series with the 1000 ohm resistors. So we're looking at 51,000 ohms. That is less than a milliamp essentially. It's like 0.12 of a milliamp of current flow. So we're going to measure and record the amount of voltage drop across the lamp. Well, with the gate signal being minimalized the way it is at 51,000 ohms, we're going to get hardly any signal to the gate, which will barely allow the lamp to glow, if at all. So here we're going to be seeing, maybe 10 volts or so across the lamp. You should measure little to no voltage across the lamp. This is due to the extremely small amount of gate current flowing through the SCR. At this point, the SCR is being triggered to pick up less than 90% or actually less than 50% of the sine wave, and will not allow much voltage of the load at all. Voltage to the load at all. You're going to decrease the resistor R1, which is our variable resistor. Doing so will increase the amount of current flow to the gate terminal and allow this SCR to start picking up the sine wave sooner. So I'm just going to scroll down to the bottom here where we have that image. Okay, so when we scroll down, we see that the SCR and the TRIAC, they act very similar in the AC circuit. So the SCR is going to be just this top half. Okay, and what we're going to see is at 50% resistance in the circuit, we're going to tell it to start triggering and picking up half of the positive pulses of the sine wave, which is this red line. We know that single phase rectifiers will hit 0 for one pulse and then pick up the second pulse once again. So that's exactly what's going on in this circuit, where we're trying to regulate power to the load or voltage to the load using an SCR in an AC circuit. So at the point where we have the resistor R1 to about 25 ohms, this will give the lamp about half brightness, measure and record the voltage across the lamp. So again, keep in mind that this is essentially a rectifier, okay? And in this rectifier, we're going to get less than half of the supply voltage as it is. So here we should only really measure 30 or 40 volts, and it will be a pulsating DC. Next, we're going to decrease the resistance of R1 to its minimum value and record the voltage across the lamp. We're going to decrease it to its minimum value, which means we're going to increase the current flow to its maximum value. Now we should see about 54 volts across the load, which is about 50% of the incoming 120 volt supply. So in procedure C, we're going to look at the TRIAC operation in an AC circuit. During this procedure, we will experiment with the TRIAC and how it is used to control voltage in an AC powered circuit. Although SCRs can be used for this application, they are not as good as TRIACs. A TRIAC is essentially two SCRs connected in parallel with the gate terminals tied together in the circuit. This is done so that the whole sine wave can be used, as the gate terminals will be triggered, allowing the whole sine wave to pass voltage through to the resistive load or a motor or something of that effect. So this one's a little bit shorter. Once the circuit has been approved and energized, you're going to turn on the S1. Okay, measure and record the voltage across lamp 1. Now for this one, it's going to be relatively consistent. We should see almost all the voltage across that load. What you will still notice if you had an oscilloscope attached to it is that the beginning and the end of the sine wave is still being clipped off a little bit. So we won't see a true 120 volts, but it'll be pretty close, maybe 105, 110. So you're going to measure and record that voltage across the load. Again, should be about 110, 115 volts. In order to get the voltage to the load for the TRIAC to vary, it would have to be a little bit more of a complex circuit where we were triggering this, the gate signal with a variable resistance to tell it where to pick up the actual sine wave. So hopefully this was helpful for you guys. If you would just review the video, email me with any questions you'd have.